Hi everyone, welcome to today's lecture on AI and evaluation, which will be asking what can we learn from the development of AI large language models. My name is Rick Davies. I'm an evaluation consultant based in Cambridge in the UK. While this is a pre-recorded presentation, I will be present with you during the lecture and I will be able to read your comments in the chat section, and I will be able to respond live to any questions during the discussion afterwards. When thinking about the topic of AI and evaluation, I have tried to identify some relevant questions. These are the 4 types of evaluation-orientated questions that I've thought might be useful to ask. Deciding on the best type of question to ask took time. Answering those questions was easier. Perhaps not surprisingly, I have sought first draft answers to these questions using AI large language models, notably Claude AI, ChatGPT, and Google Gemini. When you have the available time, you might like to explore the answers to the same set of questions using your own preferred large language model, and then perhaps compare what you have found with what I'll be talking about in this presentation. But I'm jumping ahead. I will now proceed with the presentation. I will start with the questions on the left, which are about evaluation within the context of AI. Here I am asking what sort of AI capabilities are being evaluated and what sort of evaluation methods are being used to do this. On the right, I'm focusing in more specifically on the use of AI in the context of evaluation. Here I'm asking which of all these AI capabilities that have been discussed could be relevant to an evaluation, and how can the use of those capabilities be evaluated. Before I proceed any further, I want to make it very clear that the focus of today's presentation is on recent developments in artificial intelligence, specifically those that involve the development of large language models since 2023. I won't be talking about the whole field of machine learning as it has been developing over recent decades and up to the year 2023. Although these are admittedly broad generalizations, I think there are some important differences between these two developments. With machine learning, most of the work there has been focusing on structured numerical data, whereas with large language models, the focus has been on unstructured text data. With machine learning, the analytical process is largely deterministic. The same output comes from the same type of analysis when it is reproduced. Whereas with large language models, the outputs of an analytical process are more probabilistic in character. They may vary from one implementation to the other. Another important difference is that large language models deal with much more multidimensional data. Each word in a body of text analyzed by a large language model is described by a vector which can have many thousands of dimensions. In the next 2 slides, you can see one categorization of AI large language model capabilities as developed by Claude AI. To summarize, the first 4 of the 6 capabilities are text understanding and analysis, knowledge integration and retrieval, reasoning and problem solving, creative and adaptive generation. I think a list like this can be of value in 2 ways. One is that it reminds us of what should still be a very surprisingly wide range of capacities, which somehow we have quickly got used to and now seem to be taking for granted, and are being perhaps even too skeptical about. The other is that a list like this may prompt us to think more flexibly and imaginatively about how we use AI for evaluation purposes. The 5th capacity in this list is perhaps the most underrated development, in the mind of the broader public at least. Yet it is providing a critical positive feedback loop into the development of large language models, enabling the apparently exponential development of their capacities. Perhaps many evaluators are not yet aware that many potentially evaluation-relevant applications can now be easily developed using spoken English descriptions of what is needed without the need for a specialist terminology. The last item on this list, which is about the interactivity of large language models, is another enormously underrated capacity. Large language models are not simply static databases from which we can retrieve data, of the kind that some evaluators might have been using up to now. Large language models are adaptive. They learn from interactions with others and improve their behavior. To gain the most from this capacity, we as human beings also need to learn how to interact most effectively with large language models. For those who might be interested, there is a relevant theoretical perspective here called the argumentative theory of reason, which argues with substantial evidence that the human capacity for effective reasoning arose through our interactions with each other, not through some inherent internal specialized resource. I now want to move on to the second of the 4 evaluation questions which I posed at the beginning of this presentation. This is a classification of types of evaluation approaches that can be taken toward AI performance, as generated by Claude AI. This one seems quite useful because it focuses on 3 main types of evaluation questions. Evaluation questions are often a starting point in the terms of reference for a commissioned evaluation. It may not be a fair comparison, but on the surface it looks potentially more useful than an off-the-shelf use of OECD DAC evaluation criteria. This is another classification of evaluation approaches generated by another AI. This typology is organized by differences in evaluation purpose. In practice, and perhaps reasonably so, it does not look too different from the previous typology, which focused on evaluation questions. The difference that I find most notable is that in this typology very little attention has been given to what the second category in the previous slide describes as extrinsic evaluation, which asks, what value does it create? Instead, categories 1 and 4 here address the behavior of evaluation categories 3 and 1 in the previous slide, respectively. What we are seeing is in effect another form of bias, where one perspective is emphasized and another is downplayed. One way of addressing this problem is either to ask a given AI to generate multiple alternative classifications, and/or to ask a number of AIs to each produce a classification. The first of these is the quickest, and in my experience can still be quite useful. This third typology of evaluation approaches focuses on differences in methodologies. The first category of automated benchmark evaluation provides reproducible, scalable assessments with minimal human intervention. They enable longitudinal tracking of model improvements and cross-model comparisons using consistent measures. The second category of human evaluation studies can capture nuanced quality judgments, subjective user experiences, and contextual appropriateness that automated measures can miss. They can provide insights into real-world utility and user satisfaction. The third category of interactive and dynamic testing methods can reveal behaviors that are invisible in single-turn tests, including consistency, memory, and adaptive reasoning. These can better approximate real-world usage patterns and interactions. The fourth category of adversarial and red team evaluation can identify forms of critical failure and safety issues before deployment. They can shed light on model robustness and potential misuse scenarios. In this next slide, I want to discuss the issue of evaluability challenges. An evaluability assessment is an assessment of the feasibility and value of doing an evaluation of some form of activity. In the slides that we've just been looking at, it looks like there already exists a comprehensive array of methods for evaluating a wide range of AI capacities. But there are also some evaluation challenges which need to be given attention. These are of 2 types. The first concerns AI capacity, which is advancing rapidly year by year and even month by month. The problem here is that many of the benchmarks which are being used to assess AI performance are becoming outdated because an increasing proportion of models can routinely achieve the highest level of performance on those benchmarks. This challenge is being met in different ways. More use is being made of adversarial approaches designed to test known areas of weakness, and more emphasis is being put on domain-specific assessments and the use of human judgments about performance in those areas. But this brings us to the second challenge. That is that human judgments are fallible. They vary between people and they have their biases, known and not yet known. Equally important, perhaps, is the possibility that humans may not be able to recognize the best answer or solution that might be identified by increasingly competent AIs. How can these challenges be addressed? There are 4 ways that I've identified so far, and probably others also being explored. The first is to use AI to assess AI performance. This is captured by the phrase AI as a judge. So, for example, Claude AI could be provided with the full text of a document and a summary of that document, perhaps produced by another AI, and then be asked to assess the quality of the summary using some specified criteria, which I will come back to later on in this presentation. The primary value of this approach is that it provides speed and standardization. The second approach is to develop hybrid systems, which combine both AI and human capacities. When using AI as a judge, there can be the option of introducing additional customized criteria identified by a human aware of the particular context in which the text has originated or is going to be used. The third approach is to use what is known in machine learning field as ensemble methods. This is where the same task is carried out multiple times with the same instructions, but by a different agent. Then the best scoring approach is selected from among these. For example, it would be easy to have more than one AI as a judge, assessing the quality of a summarization. The fourth approach is to treat forecasting of future events as the intelligence test that matters. What happens in the future is by definition not going to be present in the data set used to train an AI. This approach is already being exploited by Profit Arena, a web application that compares how well various AIs are in the ability to compete with humans in what are known as prediction markets, in the prediction of specific events known to be likely or observable, such as elections or the performance of economies. I now want to move the focus over from a discussion of AI in general to its use as a tool by evaluators, and then more specifically by myself. This slide provides a bridge. It describes 5 different ways in which AI has been used to evaluate social programs. The first of these is for qualitative data analysis. Evaluations can generate huge amounts of unstructured text which needs analysis. The second is for document synthesis and literature reviews. Evaluation reports themselves often need to be summarized and synthesized for wider purposes. The third is for survey design and translation purposes. The fourth is for predictive analytics purposes, in combination with older traditional machine learning approaches to identify good predictive models of outcomes of interest. And the fifth is to provide real-time analyses of feedback being generated by programs on an ongoing basis, using data from mobile phone apps and text messaging systems, for example. I will be focusing on the first category, with examples from my own work which fit primarily into the category of qualitative data analysis. Over the last 5 years, I have been working with a number of organizations to help them identify a range of possible futures that they may have to deal with. This has been done using a web application known as Parivo. It enables a group of people in different locations to collectively develop a branching tree structure of stories about what might happen in the future. In this diagram, you can see one node at the top, representing the beginning of those stories. Immediately below that is a row of 12 nodes, representing 12 different narrative descriptions of what might happen in the next time period, for example, in the following year. In each row below that are further developments of different versions of those alternative futures. The lines you can see between nodes represent different storylines, a connected sequence of events taking place further and further into the future. Unlike the purpose of forecasting future events, the purpose of the use of PAREVO is to enable preparedness rather than prediction. The assumption here is that while predicting the future is difficult, it is possible to anticipate different possible futures with varying degrees of likelihood and desirability, and then to plan how to possibly respond to each of those different kinds of futures. Each of the storylines you can see in this tree structure can be considered as a theory of change, varying in their likelihood and desirability and in other characteristics. A PAREVO exercise generates a large body of text, which can be very time-consuming to analyze on a manual basis. What I'll be talking about here is about 3 different types of text analyses that can be carried out with the assistance of AI and how its use can be evaluated. In the context of using PAREVO to explore alternative futures, I have been interested in 3 types of analysis of the text contents that are generated. The first is summarization. What I want to do here is to be able to condense a whole storyline of what might be up to 2,500 words into a much more compact summary that can be used for communication purposes to describe to participants and other stakeholders in the process the essence of each of these future scenarios. The second is text extraction. What is often of interest to organizations using PAREVO is to identify who the actors are in the storylines that have been generated, the kinds of relationships between them, and how these have changed over time. It is quite easy with a well-designed AI prompt to extract the names of organizations and individuals, and to get descriptions of the kinds of relationships between these. It is also possible to get this data structured in a way that can be immediately visualized as an annotated network diagram. The third purpose is classification. I usually want to do this in 2 ways. The first is after each iteration, when I want to identify key differences in the ways in which the stories have developed in that time period. The second is after the completion of the exercise as a whole, when there might have been up to 8 iterations altogether. At this point, I want to identify key differences in the whole storylines. While identifying key differences within the stories in a particular iteration is something that can be done manually without too much effort, comparing key differences in whole storylines on a manual basis is much more challenging and time-consuming. This is where the option of using AI is particularly valuable. In this slide, I have listed some of the different ways of evaluating the results of AI-assisted text extraction with the assistance of an AI inquiry about this issue. 3 different approaches have been identified. The first is human-based evaluation. Here, a secondary distinction is made between 2 subtypes. The first is attempts which are comprehensive and try to assess the results by identifying both what is missing but also what has been erroneously included, and by giving a summary score to the results. The second type of human-based approach is more economical and uses heuristics, in other words, simple checks of things like whether the format is as expected, whether there are any internal contradictions in the results, and whether the ways in which the extracted entities have been described in ways that fit expected categories. The second broad category is the use of AI as a judge approaches. I have not used this approach, but I can conceive of how you could set up a prompt to do both of the human tasks of comprehensive and shorthand checks. The third broad category looks at agreement between assessments, both agreement between multiple humans who might be rating the results, and also agreement between multiple AI's responses to the same extraction prompt. The measure of performance here is the degree of agreement between these multiple measurements. The second type of analysis which I want to talk about here is text summarization. Here 2 types of methods have been differentiated, similar to the previous slide. The first is manual methods of different kinds. A summarization prompt could include the requirement to reference sources for each statement in the summary. These could then be checked by a reviewer. When a summary is being read, a reviewer could check to see if the summary includes events from each iteration in the storyline's development. And the reviewer could pay particular attention to how the final events in the storyline are described in the summary. The second category of methods is using AI as a judge, as mentioned previously. The available literature suggests there are three widely used criteria here: relevance, faithfulness, and coherence. The first two of these capture classification type errors. False positives are where the content which is included doesn't exist in the original source, and false negatives where the content in the original source is not captured in the summary. The third criteria of coherence is more about readability in grammatical and logical terms. Results of an AI as a judge summarization assessment can be presented in different ways. Rating scales can be used and then supported by detailed annotations of all the types of errors identified. Comparisons can also be made with alternative summarizations where they have been generated. I thought it would be useful to share this supporting slide relating to text summarization criteria. This was generated by a quick follow-up inquiry that I made using Claude AI to find whether there are any other alternative or supplementary criteria that could be used for evaluating the results of text summarization. I won't read through each of these, but I suggest you quickly scan them now. You will be able to access this list later on when a link to this presentation is shared to all participants. I must say, I was surprised at the range of possibly relevant criteria. I now want to focus on the third type of analysis, which is text classification. This has been of special interest to me because of the potential use of the results for planning purposes. What you can see here is a 2x2 matrix of a kind which is widely used in foresight exercises. That is, exercises designed to explore alternative futures and how they can be responded to. The two dimensions of the matrix are predefined, and the immediate analytical task is to identify which par-evo generated futures belong to each of the four categories in the matrix. That classification exercise can be done in two ways. It can be done by the participants in the par-evo exercise themselves, who tag their contributions in terms of likelihood and desirability. And it can be done independently using an AI like Claude or ChatGPT. And of course, the results of each of these two different types of methods can be compared to each other for consistency. Consistency between different classification results can be measured using a confusion matrix measures and other specialist measures known as Cohen's kappa, which I won't go into here, but which you can easily search for. Accurate classifications of alternative futures into this matrix are important because each of those futures is a detailed case example which can be reflected upon as a type of future which will need to be responded to in different ways. The four main types of responses are shown in the matrix. What you can see here is a different kind of text classification using a tree structure rather than a matrix. The green nodes in the tree describe 12 different types of alternative futures generated in a par-evo exercise. At the top of the tree, you can see a binary distinction between two different types of futures. In this example, they are between societal futures where there is some form of systems breakdown on the one hand and some form of adaptive evolution on the other. Under each of these categories are further binary subdistinctions describing more specific differences between alternative futures. This type of nested categorization can be generated by humans and by AI. Human construction of this type of classification can be very time-consuming, but it can also be very informative if the participants are sharing their thoughts as they complete the sorting task. On the other hand, an AI-generated structure like this can be generated very quickly. However, thought needs to be given as to whether the sorting criteria ought to be inductively identified by the AI itself or predefined by humans. My current preference is a hybrid inductive approach, where the prompt asks the AI to identify multiple sorting criteria at each branch of the tree and then allows the human to choose which of those to implement as the sorting criteria. The kinds of differences I am looking for as sorting criteria are differences that make a difference. In other words, differences that have consequences. This type of tree structure has multiple important potential uses. Firstly, a tree classification like this provides a compact, multi-dimensional description. There are 18 different criteria in 12 combinations describing 12 different alternative futures. Secondly, the structure of the tree provides a macro, meso, and micro level perspective. The macro level perspective is at the top of the tree where the first binary distinction is introduced. The meso level perspective is provided in the middle level of the tree, and the micro level perspective can be seen at the leaf level at the bottom. Thirdly, the binary structure of the tree provides a simple choice structure that can be useful for planning purposes. At each branching point, questions can be asked about relative preferences, resource allocations, achievements, and proposed responses, and answers can be given in numerical, ranking, or text descriptive forms. Evaluation of a tree structure like this can be done in multiple ways. Firstly, as suggested already, the accuracy of the text classification can be assessed by comparing classifications within this structure by different parties, human and/or AI. Secondly, the category descriptions, which can come with supporting annotations, can be assessed as a form of text summarization. And thirdly, the overall structure can be assessed in terms of its usability as a planning device by assessing the operationalizable consequences that it might help identify. In this last slide, I want to end with some reflections on the key ideas that seem to have come to the surface in the process of developing this presentation. Looking over the presentation as a whole, there are 4 ideas which seem to be widely relevant. The first is the idea of collective intelligence, the value of working with a population of diverse agents or solutions, rather than only one. The second is the idea of hybrid intelligence, the value of combining human input and/or oversight into the implementation of an AI prompt. The third is the idea of hierarchies of capabilities, not just identifying different AI capabilities that can work in different contexts, but different AI capacities for working with other AI outputs, such as AI as a judge. The fourth is the idea of different types of knowledge structures and the merits of thinking about different forms of classification and how they can be used. Thank you for your time listening to this presentation. I hope the questions that I've asked have been of interest, and I encourage you to now make your own explorations of those using different AI large language models.